Hi everyone. Today we're going over how to do a drop test simulation in SolidWorks. It's a very simple simulation, in my opinion. It's very similar to the static linear studies we've been doing so far. We've done last class actually with Milton. So essentially, let's look at our agenda. All right, so we're gonna be going over how to make a simple part. As you saw earlier, it's the cube. We're gonna make a simple cube and then go over how to do a drop test simulation with that simple part. Then we'll go over how to quickly how dropping on its side is different, slightly different from dropping on its edge. How that gives you different results. It's pretty intuitive, honestly, but essentially dropping onto its edge is hard to calculate, hard for us to validate or like verify the results. We'll also be going over the mathematical calculations again to validate the results that we get in SolidWorks. Milton wants us to have some math calculation justifications for our results that we obtain in SolidWorks simulations. Then we'll go over how to animate our results, as well as going over ISO clippings, which really helps us visualize like where the stresses are, where the strain is, as well as where the deformations are, I believe. So it helps you better visualize which parts of the, which areas of the part, which sections of the part experiences most or more of a certain parameter. So like stress, for example. Lastly, we'll be going over how to do a drop test simulation with assemblies. Assemblies are slightly more complicated because they're consisting of multiple parts, usually. So to test assemblies, the difference is that we'll have to add some local connections. Otherwise, they'll treat each part separately, and we don't want that. We want to have local connections so we can see the effect of dropping an assembly on one part and see how having that one part affect the other parts in your assembly. And lastly, we'll go over section clippings, which also, similar to ISO clippings, help you better visualize where your assembly part is experiencing the most stress or strain or some other parameter that you're looking for. So let's start by just dragging this over. Okay. Oh, SolidWorks. So we're gonna be making this part. I'm gonna quickly walk through how to do it. It's pretty simple. How to do it, as well as how to start the drop test simulation. So again, let's just quickly sketch something. Okay, center rectangle. Doesn't really matter how much, but I just did 50-50, 50 meters, 50 millimeters, excuse me, in both dimensions, in both length and width. Okay, we can just feature, extrude that. Let's make it into a perfect 50-50 cube. Actually, let's do cube, yeah. So I already named my other cube block. So in this case, we can just name our new cube. Very intuitive, I know. So let's do cube, save in my drop test simulation folder. Try to make a folder for your simulations. It's honestly very, very useful because saving your simulations will result in a lot of different other files being saved into your folder. So if you don't save your simulation part or assembly file in a different folder, your main folder is going to be saturated and like overloaded with a bunch of simulation result files that you can't really open, but SolidWorks assembly needs to basically like retain the results. So if you double click on an old assembly that you've done simulations with, all those simulations will be saved. Actually, if you keep those extra files that SolidWorks saves in your current current folder. So you'd want to save your simulation part in its own folder or in a designated folder where you put all your simulations in. All right, so now that we have a cube, it's pretty simple. Go to simulation tab as always. That's how we do it. That's how we start any simulation. Start new study. Name here. Let's do something that's simple, but intuitive as always. So it's easy for us to identify. Excuse me. That freaking creamer and coffee. All right, so let's go down to the bottom, and under specialized simulations, there's drop test study, right? Drop test simulation. So if we check here, and now we have the simulation side command manager sidebar, whatever. So actually, I forgot to add a material here. So let's just quickly add it. It doesn't really matter what material we choose, but I believe I previously did. Let me go back to my previous block. Stainless steel or cast iron, yep, cast stainless steel. Go back to our current cube. Make sure to save. You don't want to lose all your results. Constantly hit Control S. Make sure your progress is being saved. In this case, I don't know if it matters that much of what we do. Let's just choose the same thing, just stay consistent. Cast stainless steel. See you, Ryan. All right, so now let's go to our study. See, the thing is, because I started my study after I set my material, right? Before I set my material, it doesn't carry over. The material properties weren't transferred over. If I start a new study from this part, then the material will automatically propagate in my simulations tab. But because I chose a material after this simulation was started, the material was, oh shoot, it is assigned. What the heck? Oh, okay, never mind then. Unless this is the wrong file. Oh, never mind. It does automatically assign. Oh, that's weird. It didn't in class for some reason, but I guess it does automatically propagate. If you set a material here, it will automatically propagate here as well. Okay, that's good to know. I guess this is a norm. Oops. So next step, we always want to find the setup. In this case, it's relatively simple. You can either choose the drop height, how high you want to drop it from, or the velocity at impact. Usually, I think deciding the drop height makes more sense because drop velocity is sort of confusing. You should have to calculate that from your drop height. So drop height makes more sense, in my opinion, but it's up to you. And then basically the second option is where you measure the height from. In this case, the centroid, which is like the middle of the volume here, or from the lowest point. Okay, and now you can choose your height, choose your units. In this case, let's do 3. See. Okay. Let's do 2. Actually. Okay, and then gravity. For gravity, you select the edge, well, rather the side that you want gravity to be normal to. In this case, you can choose the target to be normal to gravity or parallel to gravity. So in this case, we want to be normal to gravity. So gravity will go up away into the plane we choose. In this case, because we're starting with just dropping it on its side, we can just click one of the sides. Or you can make a plane and click on the plane that's parallel to the side. So make sure the arrow is facing the right direction. The arrow basically determines which way it's falling. In this case, it doesn't really matter which way it's falling. So I can just click check. But usually you want the arrow to be facing the direction of the plane you chose. On the bottom here, there's basically other parameters you can choose, such as like, it's more the parameters regarding the surface that your parts or assembly is falling onto, and whether there's damping. So you can choose different roughnesses, I think, stiffnesses, and frictions. There you go. I typically don't touch these. I just assume it's a rigid surface, rigid target. And to check, and we completed our setup. It's pretty simple. Then we create a mesh to discretize. Again, what Milton said was to discretize, basically break up our part into smaller chunks. So we create mesh, decide your mesh density. Usually the default option is pretty good. So I just hit check. And for simple parts, for a simple part like this cube here, we don't really need to add any more meshing than this. If we want to if we want to make a certain section of the part more accurate, we can always add a mesh control. And that way you can select an edge or a side to more finely discretize the parts. So you can make some parts of the mesh more detailed than the others, and that will give you more accurate results. In this case, it shows a cube we're dropping on its entire side to large areas. So we don't really need to bother about accuracy that much. It's also a pretty big part. It's 5 centimeters by 5 centimeters by 5 centimeters. So it's good as is. And then we hit run this study. So the reason why I had the other cubes stuff pulled up, the other block simulation pulled up, is because these things do take a while. They take at least like a minute or two, and upwards of like 5, 6, 10 minutes based on your computer, based on other conditions, based on the complexity of your part / assembly. So it's not always fun waiting for these. You can just do something else while the simulation is going on. Now for us, let's go back to our Word document. Okay, so we've gone over how to make a cube and how to conduct a drop test with the cube with a simple part, right? So now we're going over how to drop the cube on its side. Then we'll go over how to drop the cube on its edge, and that will give, understandably, higher numbers for like basically all these parameters. Again, when something's dropped on its edge or point, there's more force concentrated on a smaller area in total. It's not like infinitesimally small or no area, because although we can't determine the area that accurately, there's obviously an area that it lands on. In a smaller area, the more stress it experiences under the same force, under the same impact / collision force. Okay, so let's see, why did I close that? Okay, Control save, always save, okay? You don't want to lose your results. SolidWorks craps out all the time. Don't want to lose your results. So in this case, as you can see, there's a splattering of different stresses throughout. For von Mises, I think I think that's how it's pronounced. That's basically, it's like a combination of stresses in all like the X, Y, Z directions or dimensions. And it's the best way for you to tell if your material, if it has a yield strength, if it will, I guess, yield or fail under the given drop conditions. So in this case, I don't think cast stainless steel has a yield strength in SolidWorks, so it's not displayed here. But I think if there is a yield strength, it usually displayed on the bottom right. I think it'll be an example later on in the video regarding that. So let's see on VCs. Okay, now strain. See, you can see the individual discretized elements very well here. Every single one of those elements has their own calculations and conditions. That's how they figure out the forces and the stresses that the part experiences in different sections of itself. Okay, now let's go over some math actually to validate the results. So here, let's go into evaluate, measure, set side. As you can see, this is 2,500 millimeters squared. That's essentially this number times 10 to negative 6 meters squared. So that's a conversion. So that'll give you 0.0025. Let's look at this side. 0.0025. Okay. Now let's go over this, the math behind this real quick. So essentially what I found was, I'm pretty rusty at physics, honestly. I found a few other examples that were more complicated. One required like the frequency of collision, like the sound it makes when it collides. Some other ones involve figuring out like the individual stresses in all dimensions to figure out the von Mises stress. But those require a lot more information and work. So I'm gonna go with something simpler for myself here. If you guys can figure out something more accurate or more complex, go for it by all means. It's honestly more impressive. So what I found was that for the formula of impact force, it can be expressed by this equation here, 0.5 times mass times the impact velocity over the collision distance. Essentially, collision distance here is like the displacement or deformation of the object after it collides into something else, a different surface. So basically how much it deforms in this case. Or you can also use, if you know the collision time, how long it collides for. I think this is more of experimental value, to be honest, or something you can figure out using other components of the equation, but we don't have force, so we can't really use this one. Unless you guys can figure something out, by all means, go for it. And given, so yeah, we need to figure out what impact velocity is, right? So to do so, the equation for figuring out impact velocity with the final velocity given initial velocity, acceleration, and the different positions, distance traveled essentially, is this equation here, this formula. So given V naught equals 0 meters per second, because it's not moving to start. So that can be just set to 0. Acceleration is just gravity, which is negative 10.8, 10 meters per second squared. You guys must all be pretty familiar with that by now, hopefully. Our final height will be 0 meters. Our initial height is whatever you choose in meters. So use your given parameters, you plug it into this formula, and you should get your impact velocity. So you have the mass, impact velocity. And once you find your deformation, which you will get from the SolidWorks results in this case, you can find the stress for that direction. So if you're wrapping it up and down in the y direction, you basically find the stress. You compare your calculations with the stress in the y direction in the simulation. And I'll show you how to do that. You can choose to look at just the stress in a certain direction. So here's some simplifications. It's always important when you're doing calculations or you're doing simulations to state specifically how you simplified it, and sometimes like why you simplified it as well. So in this case, we'll use the max information from the simulation because this is sort of hard to find. The collision distance is hard to find if you don't do some real life testing, or if you don't use some simulation like SolidWorks simulation. We'll also ignore other factors for the average force, such as air resistance and drag. We just assume that there's no friction basically falling through the air. Again, the von Mises stress from SolidWorks, it's the default output, incorporates the stresses in all directions. But because we are only calculating stress in one direction here, from the force, from the up and down force, basically, we'll only be looking at the stress in one dimension, or one direction in this case. And then we'll try to look at, again, stress from one direction whenever possible, because that's what our calculations have determined so far. Let's see. Yeah, so once again, like the von Mises stress requires, the formula from von Mises stress actually involves all the other, if you look at the formula of calculating von Mises stress, you'll see that it's like it stresses in all the different directions. And so that's, first of all, a lot of calculation to do. And I think it's a lot more complex. I don't know if it's possible, I haven't tried it yet, but this is just a simpler thing we can try to do to validate our results. Here's the table I set up with macros, as you can see up here, to basically replicate these formulas. All you need to do is enter in a few parameters, and it will give me the average force and the stress. Okay, so in this case, for our cube simulation, for our first cube simulation, let's go back. Okay, in this case, we can change. Okay, so we went over math calculations. So now we can change the when we see stress. If you right click the stress one result, okay, I'll do it again. Stress one, right click, go into edit definition. It's pretty useful. Edit definition, and then here you can change what it's displaying. In this case, we can see that it's falling in the z direction, I believe. So we make sure we hit z normal stress and choose the units that you prefer. In this case, we want Newton per meter squared, and that's, I'm pretty sure, pascals. You can leave everything else the same. Oh, while we're at it, I think we might want to just click this. Oh, never mind. Okay, just ignore that. I was just curious what that did. Okay. Let me just double check to make sure the cube is falling in the z direction. Ah, never mind. The cube is falling in the y direction. Aha. Let me go ahead and change that. Right click, edit definition. So we don't want to search in the z direction if the cube is falling in the y direction, because we want to see like the stress resulting from it falling, making impact onto the ground, and like almost like compressing a little bit as it falls to the ground. So change that to the y, normal stress. Okay. So now, go back to our Excel sheet. We see that from our calculations, cube one, from a height of 2 meters, we get velocity from this formula. We get velocity of roughly 6.3 meters per second. The mass is 0.62 kilograms. If you're in kilograms, not grams. We figured that out by going to mass properties. It'll tell you the mass of your part or assembly. Go back to the Excel sheet. So here's the deformation. We get 1.7 times 10 to the negative fourth. In this case, let's go back to make sure that's the correct displacement in the y direction. Again, we're just looking at the y direction for now. And this is also why I wanted to make a distinction between falling, making impact on its edges and corners compared to making impact on its side. When you're doing the job test study with the part or assembly falling on an edge or corner, it's hard to determine exactly what the area is. If you do, it's a very, very high number, and it's not always accurate because it's very sensitive. It changes greatly as the decimal place gets smaller because stress is force over area. So as the area gets smaller and smaller, even like a factor of 10 can give you a really large difference in your final stress, obviously, in your calculated stress. So again, let's go into in the y direction, millimeters. In this case, we want meters to stay consistent. So we here got max is 1.7 times 10 to the -4th. I typically just use max to be safe. It's better to overcalculate than undercalculate, in my opinion, whether something fails or not. But we don't overcalculate for too much, obviously. So here we see roughly, 1.7 times 10 to the -4th. We get an average force of, let's see, 1.1 times 10 to the 5. 1.1 times 10 to the 5 with an area of 0.0025. As we said before, the area was what, 2,500 millimeters squared. That converts to this meter squared. And we get a result of 4.44 times 10 to the 7th. Let's go back to our y stress. Okay. So as you can see, it goes from positive high value to, first of all, make sure the unit is correct. Newtons per meter squared. Okay, cool, pascals. Now we look at the scale. It goes from very high positive to very high negative. In this case, the direction, the signage doesn't really matter. We're more concerned with the magnitude. So in this case, we just look for the higher magnitude. In this case, it's 1.6 times 10 to the 8th. And as you can see that our results are not completely lined up, obviously, because we made a lot of simplifications in obtaining our results, but it's somewhat close. 4.4 times 10 to the 7th. It's somewhere around here, the green area. So it's this area and above. Their maximum stress is like doubled our calculated stress, which is whatever. You can't get it to be complete matching. That requires a lot of work and calculations. That's why it takes the SolidWorks simulation program like minutes to calculate. And that's why we aren't doing the calculations ourselves. We're simulating it in SolidWorks because it's just much faster and much more efficient for this program to do it. Now, something cool, let's go into ISO clippings. So this is how you first, actually, let's animate it real quick. So when you animate it, it usually automatically takes like the steps for you. It'll automatically pick out like the time points. It will calculate the stress and strain of your cube. So in this case, it's using 25 frames, all the parameters here. I usually just leave it untouched. I honestly I normally don't even export this animation. I just open it and look at it for sake of like understanding what's going on understanding better what's going on with the parts, with how the impact affects the parts. And it's just cool, honestly, to just look at like what happens to the cube when it is making impact with the ground at a certain height. You can also double left click displacement. You can animate other parameters as well. In this case, we're animating the displacement. So in this case, because we're dropping only from 2 meters, the changes in, because the values of the deformation are so small, we can't really see the changes in, we can't really visually see the changes in the cube's dimensions. So in this case, we want to go into edit definition again. If you want to edit any of these parameters, you want to go to edit definition. So instead of hitting true scale, basically hitting something true scale bubble makes it so that what you see here is what the cube will actually look like pretty much after it is dropped from whatever parameters you choose. However, if we choose automatic, it will choose, SolidWorks simulation will choose what it thinks is a fitting scale to scale up the deformation or to scale up the strain so that it's more visually easy for us to understand. So let's click check. In this case, it's scaled by 24 times, which means now if we go into animate, it's much cooler. It's much more visual. We can see much easily what's going on. So as you can see, okay. So there's some like flexing going on in the shape. It's pretty cool. So in this case, it's bouncing back up. Okay, same with stress. I'm pretty sure you can also change the scale at which the visuals are propagated. Automatic is 29 times as well. In this case, if you animate this again, you'll see that the results are much, well, in this case, it's not the most different. I guess it's more so for the displacement that you can choose to have a higher scale to better visualize the parts. Here, you can see that the SolidWorks simulation took 25 plot steps, basically. It calculated at 25 points of the impact. If you click these two blue arrows, you can go back to 1 or go back to 2, and then go up to 25. You can choose the number of plot steps you want to calculate it for. Obviously, it'll take longer to calculate more plot steps. You can have more, like, I guess, accuracy, or you can tell what's going on over a longer time or with more specificity. In this case, let's see. Cool. Okay, stress. So also, it's important to see that like the overall stresses, it differs based on which time point you look at, essentially. As you can see, it's hitting somewhere in 10 to the 8th power, somewhere in that magnitude throughout most of the simulation. So our results still roughly hold up. Our results are definitely more accurate for some plot steps than others, but what can you do? All right, so that took a while, but it's all good. Now let's go back to the other pre-made simulations I've done already. All right, so this one. For the first drop test I did, again, you can have multiple drop tests, multiple simulations open at the same time. It's all on the bottom tab here. If you want to make changes to your model, you go into your models tab on the bottom here. Now you can go into sketch and do all the things you have learned and loved. Okay, now going to cube drop test 1. This is the one we did basically for, this is basically the one we just did. Dropping it onto one side of the cube. Okay, screw that. Let's see if we can open this. Okay, there you go. This is the ISO clipping. Oh, shoot, I forgot to show you guys what ISO clipping is. Nuts. Okay, let me control O. Wait, control O, date modified, cube. It's all good, guys. It's all good. Okay, so go back to your simulation. It's on the bottom tab here. Well, if you go into any of these, right, and hit right click, double click first to make sure it propagates in your main screen to make sure it shows up. Make sure it's bolded basically. If you don't select it first before you right click, you won't get all the results. For example, see, these are your results. If you click on displacement, which we're not on right now, but if you click on stress, which we are on right now, we get all of these different options. We can choose, we can go from there. So let's choose ISO clippings. Basically what this is, it's very cool. You can choose a cutoff, right? A cutoff point for the SolidWorks simulation environment to choose all the sections that are either above or below the cutoff point. And to choose above or below, you hit this button here. As you can see, it's like the inverse, right? These are all, I think, above this number here, and these are all below this number here. So in this case, if we look at, it's another part of the validation process, honestly. Once you calculate our stress, you can plug that into the ISO clipping. In this case, it's 4.44 times 10 to the 7. 4.44, E 10 to the 7th. E is 10 to the, so 4.44 times 10 to the 7th. Hit side, make sure it registers. All right, this is plus step 21, right? Let's go to 20. One above, so one above this number. All right, so hit check, and let's go back to plot step, the last plot step. All right, as you can see here, we dropped it on this side, and as you can see, the results are a little bit, I guess, accurate. So the stresses experienced in these areas are higher than what we calculated. So obviously, if you go through different plot steps, there'll be plot steps where our results are more accurate, and there are plot steps where our results are less accurate. If you click this too fast, it'll bring up the chart options. Don't want that. Okay. So as you can see, the stresses are shifting throughout the part as it makes collision, as it makes impact. Yeah, since it's 24, 25. It's somewhat accurate, basically. Our calculations are in the ballpark of what simulation achieved. And to turn this off, you need to go back to ISO clipping again, right click on your bolded selection, hit edit definition. Shoot, you don't hit edit definition, you hit ISO clipping, and then you go into this, you click on this thingy to turn it on and off. All right, now let's actually go back to our other part. All right, so here is the one we just did. Here is something else I did. Here, this is dropping the cube on its side. So in this case, to make calculations easier for myself, something you can do as well to make calculations easier for yourself as well, because dropping on an edge here, let me show you, dropping on an edge, hello? All right, so this edge here, I believe, is not chamfered. Zoom in a lot. Yes, not chamfered. So as you can see in this case, go back. But if you look at, first of all, when you click on stress, right, you can't really make it display stress in one axis, in one direction. You can't hit X normal stress or Y normal stress or Z normal stress because this cube is oriented such that the direction it's falling in is not aligned with the X, Y, or Z direction by themselves. And so as well as the fact that you can't really find the area of this line, right? It's an edge. So that's a like a 1D, yeah, like a 1D thing. There's no area associated with this, just a length. So you can't really use our formula for this. And so the workaround that I found that works a little bit is just to make a chamfer, a decent sized chamfer, and have the object fall onto the chamfer itself. So when you do want to fall on an edge, right, you can't really select the edge as a direction of gravity. That's just very inconvenient. The gravity will go along the edge instead of normal to the edge. So instead, what you want to do is make a plane. Make the plane angled at the angle that you want this object to fall on. So in this case, we want the object to fall like this, right? Normal to this plane here. Gravity will be going into this plane. As you can see now, set up, this is exactly what we have in this case. Well, that plane in this case, but in the other simulation, we'll have it falling onto this plane instead. So this is the simulation with the chamfer. You can see that I made a pretty significant chamfer here. I can just use that area to calculate stress in this direction. It won't be completely accurate because I'll be comparing it to the von Mises stress, since once again, the direction it's falling in, it's not really aligned perfectly with any one of these axes. So as you can see here, drop from the lowest point, 5 meters. Plane 2 is my gravity. I don't change the gravity value at all. Doesn't make sense to change that. Just make sure the arrow is facing the right direction. Check. Okay. And the results I got were pretty interesting, actually. Let's see if I actually have my Excel document. I believe this is it. So it had an area of this. It's maybe a little bit off, actually. Let me check my area. Let's get rid of this one. What we just did. Going to evaluate, hit measure, select the surface, give the area 70.71 millimeters squared. So in this case, we had multiplied this by 10 to the negative 6. It's 0.00007071. Excuse me. Okay, so this is not completely accurate. All right, I think this is better. So this is our initial, this was our first one, remember? And this is our second one, with the chamfer falling onto its edge and from a higher height as well. So that impact velocity is much higher. The weight is the same. Definition we got from, I also got from the simulation, which is displacement right here, roughly 1.4 times 10 to the negative 5. It gives you a force average impact force of this. And then over this surface area, we get a stress of roughly 4.77 to the 10th power, 4.77 to the 10th power. So that's a very, very high value, actually. As you can see, the value we get from the simulation is much lower. So again, it's not accurate whatsoever, pretty much, when it's falling onto its side, even with the chamfer. I think it will be more accurate with larger chamfers, but with smaller chamfers, it's similar to just falling on an edge. It gives we can't really calculate it very accurately. We have to rely more on SolidWorks. And trust that its simulation is correct. Let me make sure the math is correct, just in case. Average. Yeah, see, like we can definitely calculate the area of like an edge of a piece of metal block because nothing's ever perfectly an edge. There's always some surface, some area for that edge, but it's going to be very, very small, which will result in a very, very high stress number, which won't be reflective or accurate relating to the simulation. I don't think this method of calculation and validation works that well for edges and corners, rather. Just making sure everything's right. Evaluate, measure, double check this area. Oops. 70.71. All right. For the next one, this result setup, this simulation setup, we have it falling away from this plane. It doesn't really matter if you're falling away or into this plane, as long as you actually, okay, so when you're falling away from this, oh, no. This is something I tried differently. I chose to try dropping it onto an even smaller chamfer, and the results were higher stress. So 1.5 times 10 to the ninth with a smaller chamfer than previously. The previous result was like, I think 1 point something to the eighth power, 1.10 to the something times 10 to the eighth power. This is something times 10 to the ninth power. So as you can see, as the chamfers get smaller, as it becomes more of an edge, the values become higher as well. And once again, our calculations are not accurate. And here it's displayed similarly with ISO clipping. You choose the cutoff, and you'll only display the area, the volumes, sections of the part that surpasses or are below that your specified volume, specified value here. So if you actually put in our value, it wouldn't be accurate. You wouldn't see anything, I believe. Yep, it's past the maximum. So again, it's not accurate, so we can't really use that as our cutoff. So we're going to define a different method of validation for that. I'll leave that up to you guys. If you guys have a better idea, let me know. Or let your friends know. It'd be pretty cool. Okay. Let's go into our last cube drop, which is on a regular edge. So there should be a theoretically perfect 1D edge with no surface area. Let's see. Results, stress 4.5 times 9 to 10, times 10 to the ninth power. Slightly higher than the mini chamfer we have on the other side. Again, it's pretty cool. You can also animate it if you want. Oh, it's lagging a little bit. Oh no. Oh no. My computer's frozen. I think I pushed it past its, oh shoot, it crashed. All right, so as you can see, you can combine ISO clippings with animate, but I guess don't do that unless you have a strong enough or good enough computer, because it just failed on me, unfortunately. This is why you always save. You don't want to go through all that setup and simulation conducting just to have it crash on you. SolidWorks should have an autosave option, but I would not always trust autosave. It's good to play it safe and just constantly save. Now let's give this like 20 minutes to boot up. Oh. Dang, it's been 40 minutes. All right. So next we're gonna go over dropping an assembly. Okay. Let's see our agenda. Go over math calculations, go over ISO clippings, go over animate, go over assembly drop test, and local connections. Okay, so we're gonna go over assembly drop tests now, as well as section clippings. Oops. So what I spent like 20 minutes making was this neat little box. Wait a minute. Home. There you go. This 2-part box I made. I might just drop this into the modules page as well. Yeah, I'll just drop it into the module page so you guys can have this thing to play with as well. Load, come on. Okay, perfect. So essentially, let's getting rid of my last mate. Suppress. Your last mate should be the mate. If you're making a box, right? Your last mate should be the one that actually closes your lid. So you can do this. So you can do this just by suppressing your last mate. It's pretty cool, right? Yeah. Imagine it closing with a hinge. I'm pretty proud of this, not gonna lie. Pretty cool. Yeah, basically I want to see what happens if I drop this on this edge, how that would affect the edge here, right? Okay, let's unsuppress our last mates. That closes the lid. We can't change this anymore. Now let's go into our first motion study. First drop test study. So you do the exact same thing, except you add some local interactions. So let me show you how, by just getting rid of the local interactions we have currently. All right, so what you do is you do the same thing as you would with a regular part. You go into setup, you select the edge you wanted to, or the direction you want gravity to be pulling this from. Choose your drop conditions, drop parameters, possibly even target parameters. Check. And then you right click on components, right click components, and you see component interaction and local interaction. So you want to make some local interactions here. I'll show you what happens when you don't do local interactions, but let's do local interactions. Left click. In this case, you can select everything manually. Like this interacts with that. This hinge, this part interacts with this. Like that part interacts with like that, or something like that. Or you make it easier for yourself and have it automatically find local interactions for you if you just pick your 2 components that you wanted to find, that you were interested in finding the local interactions between. In that case, you hit find local interactions. You can see if you go over all this. Okay, there's a local interaction between the top lid contact with the lip of the box. See that there's this pin interaction with the pin holder with the hole. You'll see contact between the top lid and the top surface, this inner lip as well. You can just go over all the individual local interactions. Now they're basically like in contact with each other, right? It knows that you can't push into each other. So when you push onto the top, it will translate the force, I guess, translate some forces through to the other components. Whoops. Yeah. Basically select the ones you want. In this case, I want all of them. And then you hit this, create local interactions. And that brings these all into, that makes all those pairs into local interactions. And now we have these local interactions. As you can see, the logo is actually really cool. It's like a rotating motor that pushes this pin up and down as it rotates. That's pretty cool. I think that's pretty illustrative of what local interactions actually mean. The force is being translated to different parts. Okay, so now what I did was I dropped it on this side, right? So essentially the force of impact is onto this surface, onto these 2 surfaces here. So let's look at the stress. In this case, it's falling in the Z axis, right? It's falling on this edge, on this side. So as you can see, 7.606, displacement 5.4 times 10 to the -1, so 0.544. Going to our calculations, I also did that. Falling from 2 meters, the mass was 0.1 kilograms. Deformation, converted into meters, of course. Average force was this. Area of the side of the box was this. It was 4,500, I believe. The combined area was 4,500. And the stress gives you 8 times 10 to the 5 newtons per meter squared. So if you look at this, stress, it goes negative around here. So it's somewhere around the cutoff, somewhere around here. If you look at displacement, you can see that the force has been translated pretty well to this backside of the container. Obviously, it makes sense that the hinge part would experience the most stresses and strains because it has finer. It's a finer part. It's a more complex interaction than just face to like surface to surface. There's this pin and hole interaction here that allows it to like open and close. Essentially, like just imagine like this place would be the first place that would break if you use this box too roughly, if you are too aggressive when using this box. So think of it like that. This is the most sensitive part of the entire assembly. So something we can do now is we can actually go, first of all, we can always animate it. It's always fun to see what happens. It's gonna fall. Boom. All right. So I think what happens is this falls, as it falls onto the surface, the top lid is being pushed up, and that's causing a lot of strain and stress for this bond right here, for this interaction here. Because there's like no gap, there's no free space here for the pin to move around. Any change that's not even between the lid and the bottom part will cause it to like pull on the material and cause a lot of stress and strain and even deformation or even failure. So let's see, into stress. So we got 8 times 10 to the 5th. If we're going to ISO clipping, section clipping, whatever. So something that's really useful in my opinion is section clippings. You can change direction you want it to propagate in. So you can either choose it to look from the back, or you can look from the front based on the different plane you choose. You can look at the cross section from either side of the plane you choose. It can be one of the given planes in the assembly, or it can be a plane that you made. So in this case, we're just gonna go with the front plane. Let's change directions. Let's pull this over a little bit. This way we can see basically a cross section of where the stresses are. All right. Sometimes it's hard to tell where exactly the maximum is. And to do that, basically go into chart options. Right click on the chart and right click. Let's close this. Right click on chart option. Right click on the chart, hit chart options, and you will get this menu here. You can hit show min and show max. Min is pretty useless, to be honest, because like we don't really care about what's the lowest stress experiences. We want to know what's the highest and when it will break. So in this case, it's pretty hidden in the middle. So after this, that's where it might be helpful to choose ISO clipping. Nope. Choose section clipping. And then bring the section clipping to roughly where the maximum is. So there we go. As you can see, it's where the, I guess, the pin is located. It's that little cylinder piece that goes into the hole that allows for rotation. That obviously it makes sense. There's a lot of like shear stress going on with this pin as the box opens and closes, as well as when the box falls onto the ground, what makes impact from most of its directions. So that's how you would locate where the highest and lowest stresses are. This would be useful when you're designing something and you want to make sure that a certain section doesn't experience too much stress that it breaks. In this case, I believe plastics also don't have yield strength, but for materials that have a yield strength, it'll display it on the bottom as well. And I think it'll also put it on the plot. It'll also put it on the chart here, on the scale here, so that you know if it passed or like which sections passes the yield strength and will fail if dropped from that height, according to the simulation. So essentially, that is pretty much it, I believe, with drop test. Again, if you can find better calculations, definitely go for it. This is something simple that I come up with. I'm really rusty with physics, so I had a little bit of struggle with this. And that's the best I could come up with. There's definitely better resources out there, but I guess this is why simulations are here for. Simulations do what we cannot easily do with pen and pencil, pen and paper, pen and pencil. Let me see if we covered everything. Go over section clippings, go over assembly job tests, local interconnections. Yeah, I think went over everything. I guess let me just show you a few neat things that I was playing around with. These are definitely not very applicable to what you guys will do. They're more for fun, things that you might want to try to get more used to SolidWorks drop test simulations. So I also did a bowl, dropping a bowl onto something, onto the ground. In this case, a rigid ground. If it will load, come on, you got this computer. You're old, but you're not that old. Come on, come on. You got this. Nice. In this case, I chose not specified. Okay. So we're going to drop test 1. I specified this as cast stainless steel. Let's change this actually. Let's change this real quick to something that has a yield strength. Okay, alloy steel. There you go. Apply. There's an alloy steel. If you change materials, it changes everything, all the results. So it'll encourage you to redo all of your simulation and to rerun your simulation. So in this case, we're setting up such that, okay, I guess it just didn't save my setup conditions. So I chose the bottom flat surface here as the plane normal to gravity. The gravity will be normal too. So gravity will be falling, gravity will be pulling this bowl down. Essentially this bowl will be falling onto its bottom here from a height of 3 meters from its low, from the surface here. So to check mesh quality, I think I already did a mesh, but you can always remesh by clicking mesh and then hitting create mesh, or you can just go into this little drop-down menu here and hit create mesh here. Either way works. Mesh density doesn't matter. I'm turning down a little bit so it's faster. The finer the mesh, the longer it will take to calculate the result in the simulation, but you get more accurate results as a result. More accurate results. Yeah. Oh man, Jacobian, that's crazy. Brings me back to the old days. Okay, mesh parameters. Now, for a curved surface, you want a curved base mesh. Otherwise, you could just go with standard mesh. But because this is curved, a curved base mesh will result in better, will yield better results. There you go. You will yield better results, result in better results. Okay, mesh, you'll see that the mesh is more radially propagated. It's not as like grid-like. It's more radial. Okay, so that's good. If you want more detail, you can always apply mesh control, which is right click on the mesh, hit mesh control. Scale on a certain area, you can increase the mesh to fine to like very high value. If you really, really care about a certain part of the results. Oh shit, what did I reset? Create mesh. Now this is, you'll get finer results here. Of course, this will take like a year longer, but you know, sometimes there's a trade-off. In this case, I don't really care about the accuracy that much, nor the specificity. So you can just stick with normal mesh. Shoot. I have to remesh. Oops. Actually, yeah, okay, mesh and run works too. So instead of separately hitting mesh and then run, you can just hit mesh and run. And they'll do both at once. Okay, so I think it didn't reset my initial, did it? It might have not reset the very fine mesh that the mesh control I made earlier. That's why it's taking this long to get 3%. Okay, so it's moving somewhat quickly. That's fine then. Sometimes the visuals are buggy. When I remove the mesh control, there's still like mesh control leftovers. I believe if I hit rebuild, oh, it didn't reset. Oh, whatever. Usually hitting rebuild would just rebuild the visuals and get rid of any glitches. If it doesn't work, mount remesh will close this file and then reopen it. Yeah, this is why I didn't want to do that many or to demonstrate that many simulations. Instead, choosing to show you guys results of those simulations because it takes a while for most of these to finish up. Basically, what you should do in these cases is go into Chrome, open it up, go into YouTube, and just watch the videos. Just wait for it to finish. Okay. Damn, it's taking a while. Here, I think we can do something else while it is loading. We're going to do a different simulation. In this case, it's cast alien steel. Let's see results. So I ran these last night, and they're still safe because all the files are still present in the folder. So stresses, in this case. Oh yeah, I have it fall. Oh, yeah. Let's check the setup. Define, right click on setup, click define edit. So I'm having it fall onto this edge here, this tangent plane to the edge. So it's making contact at one point basically as it's falling. As it collides, it makes impact. In this case, it doesn't really make sense to look at the Y stress because it's not perfectly aligned with the Y axis as always. So just change into the default von Mises. You can see here, this is more accurate representation. So it experiences a lot of stress at the few points of collision here. You can always go into ISO clipping. I think that's very, very good to visualize, to help you visualize where the stress or strain is located. And in this case, it's mostly on this side of the bowl where contact is being made. If you set the bar even higher, it's just the point that it makes contact with the ground, roughly the point where it makes contact with the ground. if you choose the other side, it'll show you, if you flip the direction, it'll show you everything below this set value, which is basically everything but what we saw earlier. And that's what we saw earlier. Okay, cool. You want to get rid of your section clipping or axle clipping, you have to go into the axle clipping itself and hide it again. All right, cool. That's pretty much it. Let's see if this is done. Holy moly. This is gonna be a while. Let's see what else. I'm gonna look at some of the other formulas that I was looking at. Von Mises stress calculation. I looked it up. Yeah, it's just not fun to calculate. So you need stress in the XY, shear stress in XY. That's one way to figure it out. I also looked at something else, I think. Easy calculation. Normal stress in X, normal stress in Y, shear stress in X and Y. I guess this is a different approach you can also take. But to figure this out, you're gonna have to figure out the normal stress and shear stress, and that's something you take from the simulation, right? So you can assume that simulation is already doing this formula or a more complicated version of this formula. And so this is sort of like cheating if you would just take the stresses to figure out the ultimate stress, the von Mises stress. Yeah, this is sort of cheating essentially because you're given like almost the end products, and then you're putting it into one more step to figure out the von Mises stress, which is most likely what the simulation is already doing. So but this is another possible approach you can take if you look into this even more, such as how to calculate the normal stresses and the shear stress. That's up to you guys. That's on you guys. Let's check the progress right now. 1%, almost done. Yeah, I definitely think that it didn't get rid of the finer mesh I made at the bottom. As you can see, the purple things are gone now. Come on. 25, 24, 93, 92, 91. Happy New Year's. All right. Let's change the definition of that. Actually, we can just stick with Y because it's falling onto this bottom surface here. All right, let's see. I guess it doesn't show the yield strength in the bottom. Interesting. Pascal's yield strength is 6.2 times 10 to the 8th. So I think it, okay, yeah. So it doesn't approach the yield strength. So it doesn't display the yield strength, I believe. Only when it surpasses the yield strength does it show the actual yield strength. I believe we'll show you an example in a little bit. So this is iso clipping displacement. As you can see, the ball relative to the original position, the results actually won't look like this because if you're going to edit definition, we're looking at the displacement through a scale of 41 times or 42 times roughly. So everything you see here is exaggerated by a factor of 42. If you look at a true scale, it shouldn't be as bad of a deformation. It's more minor deformation that's less visually like obvious. That's why they put a factor of magnification onto this displacement. Okay, stress, same thing. Iso clippings, turn off. Check. Section clipping turn on. Look at different sections. All right, cool. Let's look at one more example. And that was pretty cool. So I made a rough bullet. And basically had it drop to the ground at like a speed, at the speed an average bullet would fly in. So let's see what happens. The experience is very high stress, obviously, especially at the bullet tip. I believe this is at, okay, this is heavily exaggerated. Let's see, edit definition. Actually, not heavily, just slightly exaggerated. It's actually pretty, the displacement is pretty notable without any factor of magnification. So let's animate this. Let's watch a bullet fly, baby. So as you can see, in this case, we want to make a plane that's coincident and normal to this bullet, to the direction of gravity, basically. So we can have the bullet travel into the plane. Nice, it's very cool. As you can see, in terms of stress, it's mostly at the tip. Right click here, chart options, and choose the maximum. You can see it's at the tip. And read this again. Oh, well, that's that. Some things you can't do together. All right, so let me just hit done, is reported, whatever. Yep, simulation is gonna be pretty intensive. So it's definitely normal for it to crash. So make sure to save. Overall, we just went over the cube, how to make a simple part, how to test, drop test simulation in SolidWorks with that simple part, going over dropping on the side versus the edge or corners, going over the math calculations for the side impact, going over ISO clippings, animate, assembly job test, as well as local connections to make sure it's more representative of real life situations. And then finally went over section clippings, as well as a few more examples. So I think that is all. Hope this helps a little bit, and take care, guys.